So let's talk about some astronomical calculations. The average radius of each of the 8 planets is shown in the table on the next screen. Let's state the radii of Mercury and Jupiter to 2 significant digits using scientific notation and the units of meters. Now, before I move on to the problem, I do want to address a couple things that you're seeing on the screen. One is this weirdo word, radii, radii. That's the plural of the word radius. The other thing is, you might be thinking, whoa, Steve, there's 9 planets. Actually, the latest thinking amongst the astronomical community is that Pluto is not really worthy of a planet designation, so the majority of the astronomical community now agrees that there's only 8 planets in our solar system, and I'm just a go with the majority kind of guy. So here's a table showing our 8 planets and their average radius in the right column. Notice that the radii are given in kilometers. And one thing we want to remember about the question that was posed to us is that we want to state our final radii in meters. So we'll have to keep that in mind. Now, clearly, we don't have any room to work the problem. So let's highlight the 2 rows that go with the planets that we're asked to work with, Mercury and Jupiter, and let's get rid of all the other clutter so we have some room to work. So let's first begin with the radius of Mercury. Well, one of the things it asked us to do is to write our radii using 2 significant digits. When you use scientific notation, the number of significant digits is the same as the number of numbers that you write in your mantissa. Now, if I used all of the digits 2, 4, 3, and 9 in my mantissa, I would have 4 significant digits. I only want 2 significant digits, so I have to think, how does 2, 4, 3, 9 round to 2 digits? Well, it rounds down because 3 is less than 5. So my mantissa is going to be 2.4, and 2,439, I would need to move the decimal point 1, 2, 3 places to the right. So this is 2.4 times 10 to the 3rd. But that's how many kilometers are in the radius. We want to know how many meters are in the radius. Now, you might know that there's 1,000 meters in a kilometer. If you didn't already know that, you know it now, because I just told you. 1,000, written in scientific notation, is 10 to the 3rd power. So let's go ahead and multiply by the conversion fraction 10 to the 3rd meters in 1 kilometer. Notice now that our units of kilometers are going to divide to 1, and I'm just going to be left with 2.4 times 10 to the 6th with a unit of meters. Let's talk about the radius of Jupiter now. So the radius of Jupiter is about, well, let's see. We know that the radius of Jupiter to the number of significant digits given in whatever table I got this information was 71,492. I want my mantissa to only have 2 significant digits. 4 is below 5. So when I round 714 down to 2 significant digits, my mantissa is just going to be 7.1. This is times, well, let's look at the number here. We need to move the decimal point 1, 2, 3, 4 places to the right. So this is times 10 to the 4th. And we already talked about the fact that there's 10 cubed meters in a kilometer. So we also need to multiply by 10 cubed. Now we're in meters. So altogether, this is 7.1 times 10 to the 7th meters. Notice that the power on 10 in the radius of Jupiter is 7, whereas the power of 10 on the radius of Mercury is only 6. Sometimes you'll hear people talk about magnitudes, and the magnitude of the number has something to do with the power of 10. Since the power on 10 is 1 more for the radius of Jupiter than for the radius of Mercury, you'll sometimes hear people say that the radius of Jupiter is 1 magnitude larger than the radius of Mercury. Now, let's use a proportion to kind of get a sense of how much bigger Jupiter is than Mercury. Suppose that Marge wants to paint a scale drawing of the planets. If she uses a diameter of 1 inch for Mercury, what diameter should Marge use for Jupiter? So I've gone ahead and created a new table, and I've gone ahead and put into the table these meter-measured radii that we just computed for Mercury and Jupiter. Now I'm about to perform some calculations using these rounded figures for the radii. And if there's any science teachers sitting out in the audience right now, they're probably freaking out a little bit. They're probably saying, I can't believe he's using these rounded numbers in future calculations. That's because when you round numbers before your final calculation, you very frequently get something called propagated error, and I think I have a pretty easy example for you to understand what this propagated error is. Let's pretend that a baseball weighs 1.44 pounds. And suppose we were asked to find to 2 significant digits the weight of 2 baseballs. Well, suppose that we first rounded the weight of 1 baseball to 2 significant digits. That would be 1.4 pounds. And when you multiply 1.4 pounds by 2, you end up with 2.8 pounds. But notice that if we use all 3 significant digits of the weight, 1.44 pounds, and multiply by 2, we end up with 2.88 pounds, which in fact rounds up to 2.9 pounds versus the 2.8 pounds that we got when we first rounded the weight before the calculation. That's called propagated error. The error we introduced by first rounding the weight was magnified when we performed future calculations. So when you take science classes, very early in the term, they're going to start talking about significant digits and how calculations affect significant digits. Lucky for you, I'm not too concerned about that right now at this point in the math class, because I just want you to get some really vague sense of the relationships between these numbers, but do be prepared to get a pretty hardcore lesson on significant digits when you do take your science courses. So using these rounded numbers, just to get a vague sense of the dimensions that Marge would have to use in her drawings, what we want to do is we want to define D to be the diameter of Jupiter in Marge's scale drawing. Remember, Marge is going to draw a scale drawing of the solar system, and she's going to draw Mercury with a diameter of 1 inch, and we want to figure out what the diameter of Jupiter needs to be. Well, this is just a proportion. Let's take the diameter of Jupiter in Marge's scale drawing, and let's divide by the real diameter of Jupiter, which is 2 times 7.1 times 10 to the 7th meters. This ratio needs to be the same as the ratio of the diameter of Mercury in Marge's scale drawing, which is 1 inch, divided by the actual diameter of Mercury, which is 2 times 2.4 times 10 to the 6th meters. This is called a proportion. Whenever you have 2 ratios equal to one another, you get a proportion. Let's go ahead and solve for D. Multiplying both sides of my equation by 2 times 7.1 times 10 to the 7th meters, I get that D is equal to 2 times 7.1 times 10 to the 7th meters over 2 times 2.4 times 10 to the 6th meters, all of this times 1 inch. Notice that my units of meters are going to divide to 1, and I am going to be left with units of inches. Notice, too, that I have a factor of 2 in the numerator, which divides with the factor of 2 in the denominator. So to get the numerical part of the diameter, all I need to do is take 7.1 times 10 to the 7th and divide by 2.4 times 10 to the 6th. Let's do that on a calculator. Now, when I was preparing this lesson, I looked at several different calculators to see how scientific notation works on several different calculators, and I noticed that if I picked up 8 different calculators at random, chances are they did scientific notation 8 different ways. So all I can do is show you how scientific notation works on the calculator that I'm working with. Hopefully you still have the manual for your calculator so you can read the directions to see how it works on your calculator. If you don't, or even if you do and you can't figure it out by yourself, get some help, either from your teacher or a math tutor, or maybe one of your friends can help you figure out how it works. But do make sure you figure out how it works on your calculator. Now on this calculator that I'm working with, I have to tell the calculator that I want it to work in scientific notation mode. The way I do that on this computer calculator is I right-click and I go to what it's called options, and then I need to go to display options and put it in scientific display. Obviously, that's not the way it's going to work on your calculator, but there might be a mode button or something like that that will give you an access to a menu that will allow you to change your calculator to scientific notation mode. Now that I'm in scientific notation mode, let's see what happens when I enter a number like 400. So I'm entering 400, and let's see what happens when I press the equal sign. Holy smokes, an E shows up, 4.E2. Well, what on earth can that possibly mean? Well, in scientific notation, 400 is the same as 4 times 10 to the 2nd power. So that E must just be some short calculator speak for times 10 to the power. Almost all calculators use E or EE in scientific notation, and that is always standing for times 10 to the power of whatever number follows the E or the EE. So, let's do the calculation that we're asked to perform. We need to take 7.1 times 10 to the 7th and divide by 2.4 times 10 to the 6th. So I start with my mantissa in the numerator, 7.1. On this calculator, the way I indicate that I'm about to use scientific notation is I press this EXP key. I saw several calculators in my stack that had that exact same key. Several other calculators had an EE key. You just need to find the proper key on your calculator. So I press EXP, there's my E that's saying that I'm going to do a power of 10. The power of 10 is 7. Let's divide that by 2.4, press my scientific notation key, and tell it that the power of 10 is 6. And let's go ahead and press equals, and we see that we get about 2.9583 times 10 to the 1st. Since I was working in 2 significant digits on my last screen, I'm going to go ahead and write down 2 significant digits here as well, even though technically I don't really have 2 significant digits of accuracy in my result. I'm going to let your science teachers explain that to you. When I round 2.958 to just 2 significant digits, that rounds up to 3.0. So I'm going to go ahead and say that D is about 3.0 times 10 to the 1st inches, which is just 30 inches. So the diameter of Jupiter in Marge's scale drawing of the solar system needs to be about 30 inches. So Mercury has a diameter of 1 inch, and Jupiter has a diameter of around 30 inches. How much bigger is that? Well, I had some free time yesterday, so I went ahead and cut out a little 1-inch Mercury. I don't know if you can see it there or not. I also cut out a Jupiter with a 30-inch diameter, and maybe this will help you see Mercury, and just see how much smaller Mercury is than Jupiter. Well, guess what? this is just a cross-section of the difference between the two planets. It turns out that Jupiter really, if you think about it in the correct way, is that much more bigger than Mercury, which we're going to see in our next example. So, the average radii of Mercury and Jupiter are shown on the next screen. Let's compute and compare the volumes of the two planets. This is the way that we're really going to get a sense of just how much bigger Jupiter is than Mercury. So when I rounded the two radii to two significant digits, Mercury was 2.4 times 10 to the 6 meters, and Jupiter was 7.1 times 10 to the 7th meters. Now, if we're going to compare the volumes, I think we're going to need to figure out what the volumes are. So we need a volume formula. Assuming that the two planets are perfect spheres, the volume formula for a sphere is that the volume equals 4/3 times pi times the radius cubed. So let's apply that formula 2 times. The volume of Mercury is about 4/3 pi times 2.4 times 10 to the 6 meters cubed. So let's get out our calculator and calculate that. So I'm going to go ahead and take my 4/3 and put it inside parentheses. And then I'm going to multiply by pi. And then I'm going to multiply by 2.4, hit my power of 10 key. My power of 10 is 6. Hit my exponent key, cube that number, and press equal, and I'm getting about 5.8 times 10 to the 19th. How about the volume of Jupiter? Well, this is going to be 4/3 times pi times 7.1 times 10 to the 7th meters cubed. So getting out my calculator, clearing away my last calculation, putting the 4/3 in parentheses. Now I need to multiply by pi. Now I need to multiply by 7.1 times 10 to the 7th, that number cubed. And this is rounding to about 1.5 times 10 to the 24th. But these volumes have units attached to them. What are the units? Well, in both cases, I had meters inside parentheses where the expression inside the parentheses is cubed. So the unit of meters is also cubed. The unit on each of these volumes is meters cubed. And the unit is just as important as the number because there's a great big difference between 1.5 times 10 to the 24th cubic meters and, for example, 1.5 times 10 to the 24th cubic inches. The units are really important. Now this question, what we want to do is we want to compare these two volumes. And the appropriate way to compare the two volumes is with a ratio. So let's make a ratio. Let's compare the volume of Jupiter with the volume of Mercury by dividing the volume of Mercury into the volume of Jupiter. Now again, I've gone ahead and put my rounded volume values into my table. So in terms of significant digits, I don't really have two significant digits in this ratio here. But I'm just trying to get some sort of sense about how much bigger Jupiter is than Mercury. And like I promise you, when you get to your science classes, your science teachers will tackle that significant digits issue with you. In this calculation, I'm just going to go ahead and say that this ratio is about the ratio of 1.5 times 10 to the 24th cubic meters to 5.8 times 10 to the 19th cubic meters. Looks like calculator time to me. So I need to take my 1.5 and put in my scientific notation, exp, that's times 10 to the 24th, and divide by 5.8, use my scientific notation key, that's times 10 to the 19th, and I'm getting about 2.6 times 10 to the 4th. What's the unit? Well, in my calculation, I had cubic meters in the numerator and cubic meters in the denominator, so they divide to 1. There is no unit on this ratio. What does 2.6 times 10 to the 4th mean in standard notation? Well, I'd need to move that decimal point 4 digits to the right. 2, 6, there's 1 digit to the right, 2 digits to the right, 3 digits to the right, 4 digits to the right. This ratio is about 26,000. The volume of Jupiter is about 26,000 times the volume of Mercury. Good golly, what does that mean? Well, let's think about it. I've gone ahead and made up a little animation with a Jupiter-like planet and a Mercury-like planet, but hopefully you're saying, you know what? That just doesn't seem very proportional to me. Doesn't look to me like you've got Jupiter 26,000 times as big as Mercury. Well, you know, on our little TV screen, there's no way that I could get you to be able to see Mercury if I really made it only 1/26,000th the size of Jupiter. But I can take this animation and help you understand what it means for Jupiter to be 26,000 times the size of Mercury. What I'm going to do is, I'm going to think of Mercury as a little marble, and I'm going to think of Jupiter as a great big spherical shaped fish tank. And I'm going to see how many marbles it's going to take to fill up this fish tank. Before I do that, I better put the fish in a safe place so it doesn't get clobbered with the marbles. So now let's take our Mercury-sized marbles and start placing them in the Jupiter-sized fish tank. How many marbles is it going to take? Well, Jupiter is 26,000 times as big as Mercury. So it would take around 26,000 Mercury-sized marbles to fill a Jupiter-sized fishbowl. And that's a lot of marbles. Now I want to talk about an example that's rooted in chemistry. The radius of a water molecule is about 0.14 nanometers. Suppose that a spherical snowball with a radius of 3 centimeters was blown up to the size of the Earth. If each water molecule in the snowball grew proportionally with the snowball, what would be the resultant radii of the water molecules? The reason I'm working this example is because, first thing, you probably didn't know what nm meant. It's a nanometer. The second thing is 0.14 nanometers is such a teeny tiny little length that it's really impossible to imagine it. But you still can get a sense of how teeny tiny it is using a proportion. What I have here is a little table that has several common metric names. We're using a unit of nanometer in our problem. A nanometer is 10 to the negative 9th meters. Some other common units you'll see are a micrometer, which is 10 to the negative 6 meters, a millimeter, which is 10 to the negative 3 meters, a centimeter, which is 10 to the negative 2nd meters, a kilometer, which is 10 cubed meters. These prefixes, they also apply to other metric units. For example, 1,000 liters is a kiloliter. 1,000 watts is a kilowatt. Look at the next word, a megameter. That's 10 to the 6 meters. You might have heard mega in the context of a computer discussion. Megabyte, that's 1,000,000 bytes. Similarly, a gigameter is 1 billion meters. So a gigabyte is 1 billion bytes. I included this last row not because you see 10 to the 24th meters all that frequently. I included it just because I have a special fondness for the name of that. That's a yottameter. And if you want to have some fun, see if you can come up with several different ways to pronounce the word yottameter. It's kind of a fun little game. But in our problem, we're not playing the yottameter game. We're playing a game involving nanometers, kilometers, and centimeters. So let's put those three rows up, and let's define r to be the radius of the molecule in meters after the snowball is blown up to the size of the Earth. So let's review the information we were given in the problem. We were told that we were starting with a snowball that has a radius of 3 centimeters. I looked it up on the internet, and 3 centimeters is a radius that's just a little bit smaller than the radius of a tennis ball. So we have a snowball that's just a little bit smaller than a tennis ball. The radius of a water molecule is 0.14 nanometers, and the radius of the Earth is about 6,400 kilometers. Now, we're going to get a sense of what this 0.14 nanometers is by making a ratio. When we make our ratio, we want all our units to go away, and that's not going to happen if we have mismatched units. So the first thing I'm going to do is I'm going to take our 3 radii, and I'm going to find their equivalent radii in terms of meters. So the radius of the snowball, we were told, is 3 centimeters. Let's go ahead and find the meter equivalent of 3 centimeters. So let's start with our 3 centimeters. And looking at the table above, we see that 1 centimeter is the same as 10 to the negative 2 meters. So 3 centimeters is the same as 3 times 10 to the negative 2 meters. Alrighty, let's take our water molecule radius and convert it to meters. So we have 0.14 nanometers. Since I want to express this radius using proper scientific notation, there's 2 things I need to attend to. One thing is I need to make my mantissa a number between 1 and 10. I can't use 0.14 because that's not between 1 and 10. So I'm going to make my mantissa 1.4. Now what do I need to do to get from 1.4 back to 0.14? I need to move the decimal point 1 digit to the left, which I can do by multiplying by 10 to the negative 1. Now looking up at my table at the top, I see that 1 nanometer is equivalent to 10 to the negative 9th meters. So I also have times 10 to the negative 9th meters. So when I simplify, I see that in terms of meters, the radius of a water molecule is 1.4 times 10 to the negative 10th meters. How about the radius of Earth? Well, I'm starting with 6,400 kilometers. 6,400 in proper scientific notation is 6.4 times 10 cubed, because 6,400 is 6,400 and 1,000 is 10 cubed. How about a kilometer? Well, my table up top tells me that 1 kilometer is equivalent to 10 cubed meters. So in simplified form, using meters and proper scientific notation, the radius of Earth is about 6.4 times 10 to the 6th meters. So what we want to do is we want to blow the snowball up so it's as big as the Earth. And we want to imagine the molecules growing at the same ratio as the snowball is growing. That's called a proportion. So I've gone ahead and typed up a proportion that we could solve to determine what the radius of the enlarged water molecule would be. There's a lot of numbers and letters here, so let me kind of make it real clear what's playing what role here. That r in the numerator is the new water molecule radius. It's the radius of the water molecule after the snowball blows up. The 1.4 times 10 to the negative 10th meters, that's the original, real, actual water molecule radius. The 6.4 times 10 to the 6th, that's the new snowball radius. The snowball is blowing up, so its radius is as big as the radius of the Earth. And our snowball originated with a 3.0 times 10 to the negative 2 meter radius. So new radius over old radius equals new radius over old radius. So let's go ahead and solve for r. r is going to be 6.4 times 10 to the 6th over 3.0 times 10 to the negative 2. I don't need to write any units there because I can see that on the right-hand side of my original equation, the fraction has units of meters over meters, which divide to 1. Now I also need to multiply by my 1.4 times 10 to the negative 10 meters. I'm doing that because one of my principles of solving equations says that if I multiply both sides of the equation by the same number, I'll get an equivalent equation. So let's get out our calculator and perform this calculation. So let's see, we've got 6.4 times 10 to the 6th power, and that needs to be divided by 3.0, which I can just enter as 3, times 10 to the negative 2 power. Something curious about this calculator is that when you want to negate a number, you hit the plus minus key after you enter the number, with one exception, and that's when you're using scientific notation. For whatever reason, I need to hit the plus minus key before I hit the 2. The only reason I'm telling you that is because your calculator might have some fluky operation just like this calculator does, so I wanted to give you a heads up in case you start banging your head against the wall when you try doing scientific calculations on your calculator. Now I need to multiply by 1.4 times 10 to the negative 10 power. And altogether, I get about 2.9867 times 10 to the negative 2. If I round that 2.9867 to two significant digits, that rounds up to 3.0. So something really curious is happening. This is about 3.0 times 10 to the negative 2 meters, but remember that 10 to the negative 2 meters is equivalent to 1 centimeter, so it turns out that the new radius of our water molecule is about 3.0 centimeters. Now, why is that so curious? That's so curious because that was the original radius of the snowball. This is a fluke. It just happened. There was nothing natural about this happening. It just turns out that if you have a snowball that has a radius of 3 centimeters and you blow it up to the size of the Earth, coincidentally, when the water molecules grow proportionally, they end up being the exact same size that the snowball was in the first place. So if the water molecule grows proportionally with the snowball, the radius of the water molecule is about 3 centimeters when the radius of the snowball is the same as Earth's radius. And an implication of that is that the ratio of a water molecule to a snowball with a radius of 3 centimeters is the same as the ratio of a snowball to the Earth. If you think about how a snowball with a radius of 3 centimeters compares to the Earth, that's the same ratio you get if you take one of those little water molecules inside the snowball and compare it to the snowball. So I kind of thought about how I could convey just how big a difference it is between the size of a snowball and the size of the Earth. And I thought back to our Jupiter and Mercury example, and to way to really get a sense of how much bigger Jupiter is than Mercury, I ended up dividing the volume of Mercury into the volume of Jupiter, and I saw that Jupiter was about 26,000 times larger than Mercury. Well, before I prepared this lesson, or while I was preparing this lesson, I performed a similar calculation comparing the volume of Earth with the volume of the snowball. And it turns out that it would take roughly 9.7 times 10 to the 24th snowballs to fill up the Earth. And that's a lot of snowballs. But it's more than just a lot of snowballs. Look at this 10 to the 24th. So that's not only a lot of snowballs, that's a yada snowball. And I think with that example, I yada turn it over to Candace so that she can work her part of the lesson.
For the last part of this lesson, I'm going to review Lesson 4 through what Ann and Steve talked about today in Lesson 8. I'm going to start by going over the rules and definitions of exponents one last time, and then work several examples. Then I'm going to review polynomials again and work examples, because as I work examples multiplying and dividing polynomials, I use some of the rules of exponents. So let's go over our rules and definitions of exponents. If m and n are integers and a, b, and c are real numbers, then first we have the product rule, which tells us when our bases are the same and we're multiplying, we can add the exponents. We have our power to a power rule. This is the case where we multiply exponents. A to the m to the nth power is a to the m times n. We have our power of a product rule that tells us the power of the product equals the product of the powers. Another way to remember this is the exponent distributes over multiplication. We have our quotient rule, and this is the rule where we can subtract exponents. A to the m divided by a to the n equals a to the m minus n. The power of a quotient rule is the rule where we remember that exponents distribute over division. For zero exponents, as long as our base is not 0, when we raise a number to the 0 power, we get 1. Our definition of negative exponents says we can simplify the expression a to the negative n by writing it as 1 over a to the positive n. Then we had some consequences of exponent rules and definitions. Remember that you have to remember the rules and definitions of exponents. If you happen to forget one of these consequences, that's not quite as important because you can go back to the rules and definitions. What these consequences help with is saving some steps. The consequences of exponent rules and definitions allow us to skip several steps in multi-step problems. One of these consequences is a over b raised to the negative m equals b over a raised to the positive m. We just need to take the reciprocal of what's inside parentheses to change the sign of the exponent outside the parentheses. This next one might look like the quotient rule to you. Notice I put a little parenthetical comment here that we usually use this when m is less than n. So when the exponent in the numerator, m in this case, is smaller than the exponent in the denominator, we can move everything to the denominator. B over m divided by b over n equals 1 over b to the n minus m. 1 over a to the negative n can be simplified most quickly by writing it as a to the positive n. So let's look at some examples using some of these rules and definitions. Let's say we want to simplify 4 to the negative 1 plus 4 to the negative 2. Here we have to think about the order of operations. The order of operations tells me to apply exponents before adding. So 4 to the negative 1 is 1/4, plus 4 to the negative 2 is 1 over 4 to the positive 2. So I have 1/4 plus 1/16. And to add these fractions, I need a common denominator. 1/4 can be written as 4/16. And when I add 1/16, I have 5/16. What if I want to simplify 12r to the 17th, t to the 15th, over negative 3r to the 7th, t to the 10th? Well, here I can start by figuring out what my coefficient is by dividing 12 by negative 3, and then I can deal with the factors of r and the factors of t. 12 divided by negative 3 is negative 4. I have 17 factors of r in the numerator and 7 factors of r in the denominator. This reduces to r to the 10th. I have 15 factors of t in the numerator and 10 factors of t in the denominator. This reduces to t to the 5th. Now let's simplify the opposite of 2 to the 0 minus 3 to the 0. In this problem, we have to think about the order of operations again. The order of operations tells us we need to apply exponents before we can subtract, but also before we can negate. So if I have the opposite of 2 to the 0, I need to find 2 to the 0 first, which is 1, and then negate that. And then I'm subtracting 3 to the 0, which is also 1. Negative 1 minus 1 is negative 2. Let's simplify negative 1 over x to the negative 5. Well, this is the same as negative 1 times 1 over x to the negative 5, which is negative 1 times x to the positive 5. That's negative x to the 5th. In a problem like this, we need to be careful and remember that a negative exponent does not ever affect the sign of its base. Some people might look at this problem and see a couple of negative signs and say, do those negatives cancel one another? And you'll remember that they don't if you always remember a negative exponent does not affect the sign of its base. Now let's simplify a to the 5th b over a to the 8th b to the negative 1, all raised to the power negative 3. There are several properties of exponents that I can apply here. Remember when we're applying the rules of exponents that there are different orders we can apply them. And as long as we apply them correctly, we should all come to the same final result. In this problem, something that I'm noticing is that I have factors of a in both the numerator and denominator. So I think I'm going to simplify what's in parentheses first and deal with that exponent of negative 3 later. So I have a to the 5th in the numerator and a to the 8th in the denominator. If I simplify that, that leaves a cubed in the denominator. I have b in the numerator and b to the negative 1 in the denominator. If I move that b to the negative 1 to the numerator, that gives me another factor of b in the numerator. So I have two factors of b in the numerator, which I write as b squared. All of this is still raised to the power negative 3. Remember, the quickest way to simplify this, to make that negative 3 exponent into a positive 3, is to take the reciprocal of what's in parentheses. So in parentheses, we change this to a cubed over b squared, and now we have this raised to the power positive 3. Exponents distribute over division, so I have a to the 3rd cubed, which is a to the 9th, over b squared cubed, which is b to the 6th. Now let's simplify negative 3x to the negative 1, y cubed, all raised to the negative 2 power, over xy to the negative 3, all raised to the negative 3 power. This time I have different exponents on the bases in the numerator and denominator. So I'm going to attack this problem a little bit differently. What I think I'll do in this problem is go ahead and distribute the exponent through the numerator and the exponent through the denominator. So in this case, I have negative 3 to the negative 2 in the numerator, x to the positive 2, y to the negative 6. In the denominator, I have x to the negative 3, y to the positive 9. Now let's concentrate on making our exponents positive. I can make that negative 3 to the negative 2 have an exponent of positive 2 by moving the factor to the denominator. So that's negative 3 squared in the denominator. I have x squared in the numerator and x to the negative 3 in the denominator. Simplifying gives me x to the 2 minus negative 3, which is x to the 2 plus 3, x to the 5th in the numerator. I have y to the negative 6 in the numerator and y to the 9th in the denominator. So I'm going to move that y to the negative 6 to the denominator, which gives me a total of 15 factors of y in the denominator. So I have x to the 5th over 9y to the 15th. Now let's write 87,000 in scientific notation. This is one of our applications of exponents. So I know in scientific notation I need my mantissa to be between 1 and 10, so I need my decimal point moved between the 8 and 7, so I have 8.7. Now I need to think about how many places I need to move the decimal point. To get from 8.7 back to the 87,000, I'd have to move the decimal 1, 2, 3, 4 places. So I need to multiply 8.7 by 10 to the fourth. Let's go the other direction. How do I write 7.3 times 10 to the negative fourth in standard notation? Well, that negative 4 exponent tells me to move the decimal 4 places to the left. So the first place to the left takes me to the left of the 7, and then I need 3 zeros for placeholders to move the entire 4 places to the left. So I have 0.00073 in standard notation. Now let's review polynomials. Let's start with a definition of polynomials. A polynomial is an expression containing one or more terms added together. The exponents on the variables in each term must be whole numbers, 0, 1, 2, 3, and so on. We had a second definition of a polynomial. We also said that a polynomial in x is a finite sum of terms of the form ax to the n, where a is a real number and n is a whole number. So we have some real number a times some whole number power of x. Is this a polynomial? 3x cubed plus x squared plus 6x minus 7. Since all of my terms are of the form some real number times x to a whole number power, even the constant, remember constants have degree 0, this negative 7 at the end can be thought of as negative 7 x to the 0. This is a polynomial with 4 terms. It's a third degree polynomial since our highest power here is 3. What about 2x to the negative 3 plus x squared plus x minus 1? Well, you should recognize quickly that this is not a polynomial because of this exponent of negative 3. Negative 3 is not a whole number. What about x to the 1/2 plus 3x minus 4? Again, you should quickly recognize this is not a polynomial because 1/2 as an exponent is not a whole number. What about negative 1/2 x cubed plus x squared y? It's okay to have negative 1/2 as a coefficient. We just want real number coefficients. This is a polynomial in 2 variables. Both terms have degree 3, x cubed and x squared y. Remember, when we have more than one variable, we add the exponents, 2 plus 1, to find the degree of the term, which is 3. This polynomial is a binomial because there are 2 terms. What about the constant 9? Well, remember, with constants, we can think of our constant as 9x to the 0, for instance. It's a 0 degree term, so this is a polynomial. It happens to be a monomial since there's only one term. What about 3x squared plus 2 over x squared? At first glance, you might think this is a polynomial because you see whole number exponents. But remember, you can't divide by a variable in a polynomial. And in fact, another way we can think of this is 3x squared plus 2x to the negative 2. So when we write this as 2x to the negative 2, we see the exponent of negative 2 is not a whole number, and this is not a polynomial. Now let's add the trinomial x squared plus 2x minus 5 and the trinomial 3x cubed minus 5x squared plus 2. Remember, when we're adding polynomials, we're just adding like terms, like we did in Math 60. So I have my first polynomial, a second degree polynomial, x squared plus 2x minus 5, plus my trinomial 3x cubed minus 5x squared plus 2, which is a second degree trinomial. The parentheses here are just for emphasis. I don't need to write parentheses. The only reason I did is to show that I'm adding 2 trinomials together. All I need to do here is look for like terms. I'm going to start with my highest degree term so I can write my simplified polynomial in descending order. So 3x cubed has an exponent of 3. That's my highest degree term. There aren't any other third degree terms to add to this. Now I'm going to look for second degree terms. In the first polynomial, I have x squared. In the second polynomial, I have minus 5x squared. Adding these together, I have minus 4x squared. Now I'm going to look for my first degree terms. In the first polynomial, I have 2x. In my second polynomial, I don't have any first degree terms, so I'm just going to write down plus 2x. Now I'm down to my 0 degree terms, which are my constants. Negative 5 in the first polynomial and 2 in the second polynomial. When I add those together, I get negative 3. Now let's subtract x squared plus 2x minus 5 from 3x cubed minus 5x squared plus 2. The trickiest part about setting up this problem is deciding which order to write our polynomials in. If I asked you to subtract 2 from 5, pretty quickly you'd probably tell me that was 3. What do you do there? 5 minus 2. So we need to start with the polynomial we're subtracting from, which is the 3x cubed minus 5x squared plus 2. Minus, because we're subtracting the polynomial x squared plus 2x minus 5. This time, my first set of parentheses aren't really needed. My second set of parentheses are essential. I need the parentheses around the polynomial I'm subtracting to remember that each term in that polynomial needs to be subtracted. So to simplify this, I'm going to start by removing parentheses. The first set of parentheses is not essential. I can just remove them. To remove that second set of parentheses, I need to distribute the negative through to each term. So I change the sign of each term. Minus x squared minus 2x plus 5. Now I can go ahead and look for like terms to combine. Starting with my highest degree term, 3x cubed, there's only one third degree term. Looking for second degree terms, I have minus 5x squared and minus x squared. Altogether, I have minus 6x squared. Looking for first degree terms, I have minus 2x, and that's it. So I'll bring down minus 2x. And then my constants, I have 2 plus 5, which is 7. Now I want to talk a little bit about multiplying polynomials. I'm going to review some of the things that we went over. I'm going to start by looking at a plus b times a minus b. Do you remember what these are called? The quantity a plus b and the quantity a minus b, these are conjugates. We have a binomial times a binomial, a two-term polynomial multiplied by a two-term polynomial. When we're multiplying two binomials together, we can use FOIL. Let's quickly review FOIL. In FOIL, we take the product of the first terms. In this case, that's a times a, which is a squared. Then we take the product of the outer terms. In this case, that's a times negative b, which is negative ab. We take the product of the inner terms. In this case, that's b times a, so plus ba. And we finally take the product of the last terms. In this case, that's b times negative b, which is negative b squared. Remember that when we are multiplying polynomials, it's a good idea to be in the habit of always writing your variables in the terms in alphabetical order. So if we look at our product of our inner terms, ba, we see this isn't in alphabetical order. It helps us to locate like terms if we write the variables in a term in alphabetical order. So let's go ahead and do that. Let's rewrite this ba as ab. When we do that, we see we have like terms, negative ab and positive ab, which add to 0. So when we add these together, we're left with a squared minus b squared. Notice this is one of our special products. When we multiply two conjugates together, we get a difference of squares. In this case, a squared minus b squared. A squared and b squared are perfect squares. We're subtracting them, thus the difference of squares. A couple of other special products that we looked at. A plus b quantity squared gives us a perfect square trinomial, a squared plus 2ab plus b squared. A minus b quantity squared, another perfect square trinomial, a squared minus 2ab plus b squared. Let's square r cubed plus t cubed. This is one of those special products. Here we should get a squared, in this case a is r cubed, plus 2ab, so 2 times r cubed, and in this case b is t cubed, plus b squared, so t cubed squared. This simplifies to r to the 6th plus 2r cubed t cubed plus t to the 6th. When you first looked at this problem, did you think about distributing that 2 to the r cubed and the t cubed? Hopefully you didn't, because exponents do not distribute over addition or subtraction. That's one of the most important things you need to remember. However, exponents do distribute over multiplication and division. Let's look at an example of exponents distributing over multiplication. Let's say we want to square r cubed times t cubed. Now, since we have multiplication inside the parentheses, we can distribute the exponent. That gives us r cubed squared t cubed squared, which simplifies to r to the 6th t to the 6th. If you don't need to show that step in between, that's great. I was just making a point here that the exponent distributes over multiplication. If it helps to show that step, go ahead and show that step just like I did. Now let's multiply k plus 1/3 m by k minus 1/3 m. You might recognize these as being conjugates. When we multiply two conjugates together, we get a difference of squares. In this case, k squared minus 1/3 m quantity squared. Simplifying that is k squared minus 1/9 m squared. Now let's multiply a cubed plus 11 by a to the 4th minus 2. Here I have a binomial times a binomial, but it doesn't look like any of the special products, so I can just go ahead and apply FOIL. The product of my first terms, a cubed times a to the 4th, is a to the 7th. The product of my outer terms, a to the 3rd times negative 2, is negative 2a to the 3rd. The product of my inner terms, 11 and a to the 4th, is 11a to the 4th. And the product of the last terms, 11 and negative 2, is negative 22. Now I don't see any like terms here to combine, but I am going to take one more step and rewrite this in descending order. That's the way answers are generally written in the back of the book. And it's important to remember that a to the 7th minus 2a cubed plus 11a to the 4th minus 22 is the same as a to the 7th plus 11a to the 4th minus 2a cubed minus 22. Now let's multiply x plus 2 by x to the 4th minus 3x plus 5. This time I have a binomial, x plus 2, multiplied by a trinomial, x to the 4th minus 3x plus 5. FOIL doesn't work here. FOIL only works when you have a binomial times a binomial. What I need to do here is multiply the x by x to the 4th by negative 3x and by 5. Then I need to multiply 2 by x to the 4th by negative 3x and by 5 and combine my like terms. So distributing the x through the second set of parentheses, I have x to the 5th minus 3x squared plus 5x. Distributing the 2 through the second set of parentheses, I have plus 2x to the 4th minus 6x plus 10. Now I need to look for like terms. I'm going to start with my highest degree terms. It looks like I just have one 5th degree term, x to the 5th. So now I'll look for 4th degree terms. I have 2x to the 4th. I don't see any 3rd degree terms. I have just the one 2nd degree term, negative 3x squared. I have two 1st degree terms, 5x and negative 6x adds up to negative 1x, which we simply write as negative x. And then just the one constant plus 10. For my last example, I want to write an algebraic expression in reduced form for the shaded region. So looking at my region here, I have this big periwinkle rectangle, which has a length of 3x plus 2 and a width of 2x minus 1. From the periwinkle rectangle, we have a little white square cut out, which has sides of length x. So if I want to find the area of this periwinkle region, I need to take the area of the rectangle minus the area of the square. So the area of the rectangle, length times width, is 3x plus 2 times 2x minus 1. Minus the area of the square would be minus x squared. I'm asked to write my algebraic expression in reduced form, so I need to go ahead and do some algebra here. At the beginning of this expression, I have a binomial times a binomial. That gives me the area of the large rectangle. Since it's a binomial times a binomial, I'll apply FOIL. 3x times 2x is 6x squared. 3x times negative 1 is negative 3x. 2 times 2x is plus 4x. 2 times negative 1 is negative 2. And finally, I have that minus x squared, which represents taking out the area of that square. Combining like terms, 6x squared minus x squared is 5x squared. Negative 3x plus 4x is plus x minus 2. So the area of the periwinkle region is 5x squared plus x minus 2. And this concludes Lesson 8.